Any questions about anything from last time? About anything? At the end of last hour, I motivated the definition of the complex exponential function based on Euler's calculations. Right now, we'll just take this to be the definition of the complex exponential. And later, I'll derive the thing sort of more from first principles. But it's nice to get rolling with this, the most important function in math at our fingertips. And several of the reasons it's the most important function in math is these key properties. Let's see, number one, e to the 0 is 1. That's easy to check. You just put in x equals 0 and y equals 0. And later on, soon, I'll verify that the complex derivative that I talked about with the complex difference quotient exists, and the derivative of e to the z is itself. And in fact, these two properties determine e to the z, kind of like if you take an ODE course, it's like e to the x. E to the x is 0. It's 1 at x equals 0, and its derivative is itself, and that completely determines that function. So these two things determine e to the z. There's only one thing that does that, and it's e to the z. We'll see that from first principles soon. Another big one is that e to the z plus w is e to the z times e to the w, just like the real exponential does when there's real variables. Okay, and so let's see. This is a math major class, so I should mention that's kind of an algebra fact. It's a group homomorphism. Let's see, so what's the group? That's mapping the additive group of complex numbers to the multiplicative group. And let's see, that multiplicative group would be C minus 0. Morphism. That's a cool fact. And of course, there's only one of those things, too. Now let's see, if I were to mess around with number 3 there, it would show that e to the minus z is 1 over e to the z. And consequently, when you look at that, you realize e to the z can never vanish. E to the z is never 0. That's nice to know. And in fact, you can see number 4 by taking number 3 and doing e to the z plus minus z. That would be e to the 0 by number 3, and e to the 0 is 1. Let's see, so what the heck? What am I trying to say? That's equal to e to the z times e to the minus z. And of course, that's e to the 0 when you add them up, and that's 1. And so I've got a product of two complex numbers that's 1. Of course, neither one of them can be 0. And therefore I can divide and see that e to the minus z is 1 over e to the z. So that's how you see that for number 3. So number 3 is the big one there to check. And I'll check it right now. Let's see. As long as I'm putting things in the list, another biggie is that follows from number 3 is de Moivre's formula. French guy's name. And that is that e to the I theta to the nth power is e to the I n theta. And that happens to be true for all integers n. So right now I'll check it for positive n, but it works for all even negative integers. Now see, I'm using number 3 here to see this. And number 3 shows this too, because e to the I theta to the n would be e to the I theta times e to the I theta n times. And let's see, I take the first 2 there and use number 3, and then I take the first 2 plus the third and do number 3 again, and keep doing it. So that would be n times. And I just keep repeating number 3, and of course I would get e to the I n theta. So I theta plus dot 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 plus I theta. And you have n of those, so it would be e to the I n theta. So 5 pops right out from that. From positive n. Actually, yeah, I'll show you why it's also true for negative n in a little bit. Any questions so far about anything? Okay. Let's see. So the big thing I want to show you, because it implies all the other stuff, is number 3. So proof of 3. Let's write e to the z times e to the w. Let's write that as z is x plus iy, and w is u plus e. Let's make w be, I'm going to save that. Let's call this step 1. Step 1 is to check that e to the I alpha plus beta is e to the I alpha times e to the I beta. Okay, the left-hand side here is cosine alpha plus beta plus I sine alpha plus beta. And the question is that equal to the product of those two things? And the product of those two things, the first one is cosine alpha plus I sine beta. Wait a minute, sine alpha. And the second one is cosine beta plus I sine beta. And I multiply that out and get, so this is question mark. Let's see, the real part is going to be cosine alpha, cosine beta. And I get another real thing when the I sine alpha hits the I sine beta, because I squared is minus 1. So this is sine alpha sine beta with a minus sign. That's the only cross terms that give me real numbers. And then the imaginary stuff would be, let's see, I'd get a cosine alpha times sine beta. And The other one would be a sine alpha cosine beta. And sure enough, those things are equal because this is the sum of angles formula from high school, cosine alpha plus beta, so check. And this is sine alpha plus beta, so check. So a fun thing I like to do, if I had more time to play around, I'll probably do it at some point, I can prove the fact about the exponential using sort of differential equation argument, ODE, like Math 262. And once you have the basic facts about the complex exponential, you can prove number 3 using calculus. And so the amazing thing is trigonometry pops out from the complex exponential. And you can get all the formulas from trig without even drawing a triangle. That's a fun exercise to do and shows you the power of complex calculus. But right now, I'll allow trigonometry to get going quickly. Questions about that? In fact, if you ever forget the sum of angles formula, doing what I did there will give it to you. See, when I realized that, I flushed all those formulas out of my head because they're so easy to derive when you need them by doing exactly this. Okay, now I can do step 2 of the demonstration of number 3. I have to allow the step 2. Let's say, so I'd have e to the x plus iy times e to the u plus iv. Of course, that's e to the x times e to the iy times e to the u times e to the iv. And the associative rule for complex multiplication, it's a field, so it holds. So that would be e to the x times e to the u. I'll put those together. Doesn't matter what order you do it. Then I'll have e to the iy times e to the iv. Of course, this is just the real exponential, so it satisfies e to the x plus u. And this is the thing I just showed you. This is e to the I y plus v. And of course, that's the definition of that's e to the x plus u definition plus I y plus v. So check. So showing it for the I term is just trig stuff, and showing it for the real part is just the basic real exponential. So when you put those two things together, it pops right out. Okay. So I told you the cool thing is that you get trig identities from algebra. And so whenever you need one, you can just do algebra, so you get trig identities via algebra. Let's see, an example would be, how about sine 2 theta? So sine 2 theta is 2 sine theta cosine theta. Okay, so how would you see that? Well, sine 2 theta is the imaginary part of e to the I 2 theta. And e to the I 2 theta is e to the I theta squared. And that would be when I write out e to the I theta is cosine theta plus I sine theta, and I square that. The real part is who cares, and the imaginary part is the imaginary part would be cosine theta times sine theta plus sine theta times cosine theta. And we see, aha, yes, that's the famous formula for the sine of 2 theta. Check. Anyway, that's something to note. So let me summarize a little bit here. We've been doing arithmetic kind of things on C. It feels just like the real numbers. So C is a field, so the algebra is very much familiar, just like the real numbers. Okay. So in particular, C is a field. All the axioms of a field hold. Associative, commutative rules, etc., distributive law, etc. Everything has an inverse. Also, C is complete. That's a fancy word in analysis. If you took Math 341, you learned that the real numbers are complete, which means that every Cauchy sequence has a limit. That's a very critical thing for the real numbers. It's also true for C. I'll talk more about limits in the complex setting soon, meaning I'll define what a Cauchy sequence is. Every Cauchy sequence in C has a limit. Or I should say converges to a limit. But an exciting thing about C that's true, that's not true for R, is that C is algebraically closed. And I'll demonstrate that in this course soon. Meaning that every polynomial has a root in C. Every polynomial in C, in a complex numbers, has a root in C. So that's the fundamental theorem of algebra I mentioned last time. And of course that's very much unlike R, because x squared plus 1 equals 0 doesn't have a root, for example. Okay. So that's the algebra of the complex numbers. And we're going to determine some of that algebra to be true by using analysis. And of course, when you're going to talk about analysis, you've got to talk about epsilons and deltas and open sets and stuff like that. So that stuff is called topology. So analysis on C will be based on the same topology. The funny thing, the algebra is the same as R, but the topology in C is the same as that of R2. So I sort of think of R2 as being identified with C by the usual picture. Okay, and let's see, as long as I'm doing the usual pictures, maybe it's a good time to dwell on it a bit. I want to talk about complex numbers in polar form. Now that we have that complex exponential, there's a very convenient way to express complex numbers via the complex exponential. Here's the basic picture. Let's take a complex number here, z equals x plus iy. Then let's call this radius r, and let's call this angle theta. And then if I project downwards here, I get the x here, and I get the y here. Okay, and let's see, the basic words are x is the real part of z, and you see it's there. In the picture, that would be r times cosine theta. And y is the imaginary part of z. You see that's equal to r sine theta. And that r is equal to the modulus. Okay, and so let's see, if I'm going to write in polar form, z is x plus iy, that would be r cosine theta plus I times r sine theta. And you realize, aha, there's the complex exponential showing up. That's r times e to the I theta. That's the polar form of a complex number. Let's see, I guess I should have written here. Okay, let's see, that's the polar form of z. And it's going to turn out to be very convenient, especially when we're going to compute complex roots of complex numbers. I'm going to do that in a second, but let me, then I mentioned last time that my favorite theta, everybody's favorite theta here, is called the principal argument of z. But there's no, I could also put other thetas in there if I wanted to. And that means I take the angle in that picture that's between pi and it's between minus pi and plus pi, and at the plus pi side I let plus pi win and minus pi lose. Okay. But I could also take any old theta. Here's my favorite notation. I like to write, this is my definition, I like to write arg of z with a little a to mean the set of all z's, of all angles. Set of all theta. With that makes that picture true. So let's see, set of all theta with z equals r e to the I theta. Of course, that r has to be the modulus of z. And if you think about that, that would be equal to the set of the principal argument of z plus any old multiple of 2 pi. So 2n pi. And n could be any old integer. Let's say maybe should draw a picture of what complex multiplication looks like now. You can see it from this polar form. So I should remark that adding complex numbers is just like vector addition. It's just vector addition. Corresponds to vector addition in R2. But multiplying them is something weird and new. The picture's kind of awkward to draw. Let's see, here's an x-axis. Let me draw one complex number here. I'll make that R2 e to the I theta 2. And that theta 2 you see in the picture looks like this. And if I have an R1 e to the I theta 1, that theta 1 looks like this. If I multiply them together, then the radius multiplies. And the angles add. That's kind of a weird thing to draw. So the thetas would be theta 1 plus theta 2. And so this is the product. So this would be the product, V times W equals R1, R2, the radii multiply, and the angles add. So let's see, this is the V, and this is the W. So there's a picture for complex multiplication, and it's something new and wild. Okay, I just need a couple more facts before I can do complex roots. Here's some easy facts from the pictures. Let's see, it's easy to check that the modulus of e to the I theta, of course that would be the square root of cosine squared plus sine squared. So e to the I theta is a point on the unit circle. And in fact, here's e to the I theta on the unit circle. As the theta goes around, you trace out the unit circle. And so that's a great way to parameterize the unit circle using just a simple notation of z of theta is e to the I theta. And so as theta increases, you're going around this in the counterclockwise sense. That's going to be a very convenient way of parametrizing the circle in complex notation. Another thing that's easy to check is that e to the minus I theta, that would be cosine minus theta plus I sine minus theta. Of course, cosine theta is an even function, and sine theta is an odd function. and that's equal to the conjugate, e to the I theta conjugate. And so let's see, we see from that yeah, that's the formula I wanted. It's also easy to see that 1 over, let's see, we have e to the I theta times e to the minus I theta is equal to 1. And so 1 over e to the I theta is e to the minus I theta. And that's exactly what you need to demonstrate the Modeller's formula. This allows you to see de Moivre's formula for n negative. Of course, they have to be natural numbers. Okay, now I'm going to finally do something. Questions about anything? I'm going to find some complex roots. And the complex exponential is very useful for that. Well, let's see. Probably the best way to demonstrate this is to just do it as an example. So let's find all the z whose fourth power, complex z, such that the fourth power is something. Let's make it be a complex number. How about 16i? Okay, so this is where the polar form of a complex number is extremely useful. Let's see. Let's write. Let's write z as r e to the I theta. And that theta doesn't necessarily have to be the principal argument. So that's my z in polar form. And I want to take that to the fourth power, and I want it to be 16i. Okay, so I've just gone through the basic facts about the de Moivre's formula, etc. That fourth power is r to the fourth times e to the I 4 theta. And I want that to be 16i. Okay, think about that. This is the polar form of a complex number on the left, and 16i is a complex number. It's convenient to write it also in polar form. So let's see. Here's the complex plane. Here's 16i right here. So the radius of 16i is 16. But this angle right here is pi over 2. Let's see, and the radius is 16. And so we can write this, I'll write it again. I have r to the fourth e to the I 4 pi, theta, equals radius 16 times e to the I pi over 2. Of course, in the polar form of a complex number, that r has to be a positive thing. And so we see that the radius thing is the obvious thing. R to the fourth has to be equal to 16. If I'd made this minus 16i, that would be a positive thing there. because I'd have a different angle, and my radius would be positive 16 if I had a minus 16i. So that's a possibility you need to take into consideration. Anyway, this one, something to note is our r is bigger than 0 in the polar form. So we deduce that r has to be the fourth root of 16, which is 2. So the positive fourth root, 16 to the 1/4, equals 2. So it's determined. That's the easy part. The angle we have to think about. We want these two polar representations to represent the same number. So it's a polar form of a complex number, and it better represent the same complex number. But that polar form is not unique. So, what do we see? So, these two polar forms need to represent the same complex number. So what does that mean? Well, certainly if 4 theta was equal to pi over 2, that's the most obvious possible way to do that. But I could go around 2 pi times and get a different solution to that. So pi over 2 is one way to represent it, but plus some multiple of 2 pi. So n is an integer. That's what it means for those two things to represent the same complex number in the plane. Those two angles have to be the same modulo multiple of 2 pi. And see, it looks like, oh my gosh, there's going to be infinitely many of these stupid things. But it turns out there's only 4. So let's solve for theta there. I get theta is equal to pi over 8 plus a multiple of pi over 2. Okay, so that's going to be the answer. Let's think about what that looks like. I would have, see if I can draw this nicely. There's the axes. Let's see, I'm going to erase this in a second. This is pathetic. Let's see. Let me do it. I'm going to erase this line in a second. 45 degrees I can draw. Half of that, okay, so this is going to be, it's pretty crummy. I'm going to try to bisect that angle. There's pi over 8. Okay, now I can erase that 45 degree line. There's pi over 8. This is radius 2, and so that would be 2e to the I pi over 8. And then if I add pi over 2 to that, I'm going to get something that's perpendicular to it. all these radii are 2. Okay, so that'd be pi over 2 is 4 pi over 8. So this would be 2e to the I 5 pi over 8. The next one would be pi over 2 more. That would be 9 pi over 8. And let's see, so I'm adding 4 every time. This would be 2 times e to the I 13 pi over 8. And the next time it would repeat. So I'd go around and around and only hit those 4 points. And if I were taking negative ends, I'd be going the other way around, clockwise instead of counterclockwise. So when you look at it like that, you realize there's only 4. There's only 4 fourth roots. Of 16i. They repeat. Questions about that? Well, I'm dying to start doing calculus now that I got some of this algebra out of the way. And so it's time to talk about topology on the complex plane. And it's the fact is, it's the same as the topology in R2. And it's a metric space topology, which is a particularly nice kind of topology. So here we are in the complex plane, which we identify with C. I mean, we identify with R2. And if I have 2 points in the complex plane here, let's take Z2 and Z1. Then this distance between them call it D. D is the distance between Z1 and Z2. That's going to be the square root of x1 minus x2 squared plus y1 minus y2 squared. That is conveniently written as the modulus of z1 minus z2. So we have a very nice way of writing that distance that doesn't involve all the ugly square roots. Okay. If you ever had a metric space topology lesson, you'd know that disks are the critical things to define open sets. So we take the disk of radius r, about a point z naught. That's going to be the set of all z such that z minus z naught is strictly less than r. That's called the open disk of radius r about z naught. And I'll stop using the word open. It's just called the disk of radius r. We always like our disks to be open disks. Open disk of radius r about z naught. And so the picture would be what you expect. So let's see, I'll draw a dotted line for the circle to indicate that the boundary's not in it. And z naught here is the point in the center, and it's a disk of radius r. And the set of points then is the shaded region inside that disk. Okay, now I can define what an open set is. The basic objects of this class are going to be complex valued functions that have a complex derivative, and they'll be defined on an open set. So a domain omega in the complex plane is called open, just like in R2, if for any point in the set there's an open disk dr z naught with R positive, of course, so not the empty disk. That's contained totally inside. And the thing to note here is that R can depend on Z naught. It's not one R works for all Z's. And so an example where it depends, I guess almost every example I draw except the whole complex plane, it would depend. So let's see, here's an open set. I'd already drew a disk. Disks are open. That you actually have to show that an open disk is actually open by this definition. One of those exercises that seems kind of dumb. This is an open set. So the shaded region, but not the dotted stuff. And if you think about what disks I put in there, this disk right about that Z naught would have to be a little tiny disk. But the disk about this point could be much bigger, etc. And this one over this corner would also have to be very tiny. And see, if you want to come up with a set that's not open, well, here's one. I could have this whole boundary in, and maybe this one out. So the set would be this boundary plus this stuff, but not that dotted stuff. And if you pick a point in there like this point right here, that's in the domain, so it's included, but I can't possibly put a disk in there. So this would be, if I try to stick a disk about this point, ouch, that disk hangs outside. I can't stick a disk in. About that red dot. Okay. So this one is open. This one is not open. Well, I'm almost ready to define the most important thing we're going to look at here. The important omegas are the ones that are path connected. So let's see, connected open sets. And when you're talking about open sets in the plane, connected is going to mean path connected. It means I can connect any 2 points in the domain by a continuous